Hello, in this video we are working on finding inverses symbolically, which means we are going to find those algebraically. We've previously worked on inverses from a graphing approach where you're given the graph of a function and you have to graph the inverses, and we talked about how you switch those x and y values and how they are a reflection over the y equals x line. So this is a continuation of what you've already learned, and I just wanted to show you some reminders here about a one-to-one function. And remember, a one-to-one function must have one value corresponds to exactly one value of x. Sorry, I did not say that clearly. One value in the output corresponds to exactly one value of the input. You can also think about it as passing that horizontal line test. And if you think it will fail the horizontal line test, then it's not a one-to-one function. Moving on here, there's some formal ways that you can think about a function being one-to-one, and one of them is to show that when you plug in x sub 1 and you plug in an x sub 2, then you can simplify the expression back down to x sub 1 equals x sub 2. So I'll show you a quick example of that, and then we'll come back to this slide here in a second. But if you look at this example 1, part A here, it says show that f of x equals 2 over x minus 3 is a one-to-one function. Well, the way that they're showing you on this next solution is they are using the method that I just discussed. They are putting in an x sub 1 and they're putting in an x sub 2, and they're simplifying the expression down. So in the function itself, you have an x in the denominator, and you can see on the left side they're replacing that with an x sub 1, and on the right side they're replacing that with an x sub 2, and then they are simplifying this expression down, and you can see the algebra is all here, and you can get it to simplify all the way down to this x sub 1 equals x sub 2 statement, like what we talked about on that previous slide. So let me go back to that, and if you can get the algebra to go down to this statement, then it is indeed a one-to-one function. Another way that you can show a one-to-one function is to find what we call a counterexample, and this is typically the way that makes more sense to a lot of students. And so if you look at this next example here, part B, it says determine if the function g of x equals x squared minus 2 is a one-to-one function. Well, if you think about g of x, all right, think about what it's going to look like. It's a quadratic, so we know those look like parabolas. And then imagine doing that horizontal line test. You know it's going to fail. So already if you just visualize g of x, you already know what you're dealing with here. But I'll show you what it means to find a counterexample. And what they did is they said, hey, what if I put in a negative 3 into the g function? And you can see that they did all the work here, and they can simplify that to a 7. And then if you put in a positive 3, you can do all the same work and get to a 7. So the fact that you have two different inputs that give you the same output means it is going to fail that horizontal line test, and it's going to fail that one-to-one test. So this is a counterexample. You're showing an example where it's not one-to-one. So going back to this here, this is just, like I said, some formal language to kind of get you thinking about the algebra behind justifying whether a function is one-to-one. The reason we have to worry about that is because when we are finding our inverse functions, we can only find an inverse if a function is indeed one-to-one. So if you have a one-to-one function, then you can find this inverse, but it must be one-to-one before you can find an inverse. So once again, it's just good to kind of understand what it means to be one-to-one and some of that background knowledge so that you can, use that knowledge to help you when you need it. We've already seen this notation before, this f to the -1, that does represent an inverse. And down here it's very formal language of what you're doing when you find these inverse functions. And like I said, you're welcome to read through that. Most students look at that and go, oh my gosh, what is she talking about? I think it makes more sense when you actually work some problems. So let's spend our time on the problems. When you are working with domain and range, and this is review, remember that your domain and range actually end up switching. So when you have the domain of a function, you plug that domain in and you get a range, okay? But then when you switch to the inverse, your range is now your domain, right? And then the domain gets you back to the range. So it's like they switch places, and that's what the arrows are showing you there, that you start with a domain, you get a range, but then the range becomes your domain, and then you use that to find the new range of the inverse function. So let's get down to the algebra here, and these are your basic steps that you want to follow when you're finding an inverse function algebraically. You want to replace your f of x with a y, then you switch your x and y, and then you solve for y, and then you rewrite your function with the inverse notation. So let's go through some problems together here. So you see we have f of x equals 3x plus 2. This is a linear function, okay? And so we can go ahead and think about the domain and range of f of x, because we know what f of x looks like, right? It's a linear function, and you can imagine graphing that function, and it's going to have negative infinity, positive infinity, and your range is going to be the same thing. Okay, and so it does tell us right up here to find the domain of each function, the function and its inverse. Okay, and so we've already found the domain of our function and our range actually. And so now let's actually find the inverse function. So first you want to think about this f of x as being a y, and then you switch your x and y variables, and then you solve for y. So I'm going to subtract 2 from both sides, and then I'm going to divide by 3. And then you take the y out and you rewrite it with the inverse notation. So you would say that f inverse of x equals x minus 2 over 3. If you wanted to simplify that 3 in, you could also write your function, inverse function, as f inverse of x is 1/3 x minus 2/3. Okay, and that would mean the same thing as what I circled there in the other version of the answer. Either one's okay, and like in WebAssign, it'll take either one. Okay. And so what we have here is another linear function, okay? So remember that when you are dealing with a function and its inverse, the domain and range just switch, okay? So my range from my function is now my domain of my inverse, and my domain of my function is now my range of my inverse. And if you can look down here, I have graphed that for you. Okay, and this solid line here, this is f of x. All right, there's that linear function. And then this bluish line is the inverse. Okay, and then this is your y equals x line. And as like I said, we've talked about in previous lesson how a function as inverse is reflected over that y equals x line. And just remember how those x and y values are switching places with each other, and that's why they look the way that they look. So if we go on to this next slide, it talks about composition of functions and how that relates to an inverse. So if you have a function and then you find its inverse, then you can take the composition of these two functions and you can always get back to x. Okay, and they were actually referring to that on our earlier slide that you may have picked up on that. So I'll just show you a quick little rendition of this. So I'm going to use those two linear functions that we had in our previous example that we were working on, and f of x was the linear function 3x plus 2, and then we found the inverse function was the x minus 2 over 3. Okay, so if I do f of f inverse, then I'm going to put the inverse function inside of f. Okay, so where there's a variable, remember we've done this before, where there's a variable you stick the function, inverse function in. So I'll have 3 times x minus 2 over 3 plus 2, and then I simplify this. The 3's will cross reduce there, and then I have x minus 2 plus 2, and that does simplify to x. And then if I work it the other way, I do f inverse of f. That means I am putting the f function inside the inverse, and we'll see what happens there. So where you have a variable in that inverse, you're going to stick the f of x function. So it'll be 3x plus 2 minus 2 over 3, and then do some simplifying. So you'll have 3x over 3, and then those 3's will reduce down, and you will get down to an x. Okay, so going back to our previous slide, it shows that, hey, if you have a function as inverse, you should always be able to take the composition and get back to just x. All right, so you can see here how we were able to use a function in its inverse and do the composition, and you can get back to x regardless of which way you do the composition. And this is another way to talk about a function and their inverse, because sometimes you're given two functions and you're just trying to figure out if they are inverse functions of each other, and so you can use your composition to answer that question. Alright, so here's another example, and we're given a g of x function, and we need to find the inverse and the domain and range, and then do the graph. So once again, we're going to follow our steps of, let's go ahead and think about the domain of g of x. So g of x, we need to think about, we have a square root here, so we need to think about that 3 minus x has to be greater than or equal to 0. And then we're going to subtract 3 from both sides and divide by the negative, and then we're going to get x has to be less than or equal to 3. And that will tell us that my domain of g of x needs to be negative infinity to 3 bracket. Okay, now for my range, you might be able to figure that out by looking at or thinking about the function or thinking about your numbers. Some people can, some people can't at this stage of the game. Like I said, later down the semester you'll get really good at this kind of stuff. We can plug in a 3 right here into the function and simplify that down, and that will tell us information about the range. But let's say you didn't know to do that, so you were kind of stuck here, and I'll show you a little trick here in just a second that you can use if you're struggling on figuring out this range. So let's find the inverse. Okay, so I'm going to put in a y, and then you switch your x and y, and then you solve for y. So I need to subtract 4 from both sides, and then I need to square both sides to get rid of that square root. We've had that before, and then I'm going to subtract 3 from both sides, and then I need to divide through by a negative. So be very careful here. You want to think about dividing all the way through by a negative on the left and the right. So I'm going to have, I'll just come up here, I'm going to have negative x minus 4 squared plus 3 equals y. And then if you wanted to rearrange that and put the 3 in the front, you could. So you could say 3 minus x minus 4 squared, but it really doesn't matter if you do that. And then lastly, let's just put that function notation in there. So this will be g inverse of x. Okay, so here is my inverse function. And what you're probably thinking about here is, hey, that's a quadratic, okay? So when we used our square root function, and when you get to squaring both sides, a lot of times you will end up with that quadratic function. So that's something that we're going to have to think about here as we progress through the problem. So when you have a g of x function, and let's go ahead and talk about the graph here real quick. So this graph here is this solid dark, I guess, black line there. That is of your g of x function. But you can see here with the inverse function that they did not graph the full parabola. Okay, and the reason for that is because of how your domain and range needs to work, and you need to keep this one-to-one relationship. So going back to your range, okay, if we have this graph, and remember you can generate your graphs from doing a table of values, right? And you know what your domain is, right? And you can just plug in some numbers. Make sure you plug in all the way up to using that 3. You will get a so we want to write our range, okay? So, and my range, the smallest range value is going to be 4, okay? And then it's going to go up from there. So that'll be 4 to infinity. So basically, you know, try to remind students that you guys know how to graph a function, you understand how to do a table of values, you understand how to find the domain, and sometimes if you will jump ahead, do your graph, that can help you to figure out your range. Okay, now let's talk about the inverse function. So for g inverse of x, remember that your domain has to match the range of the g of x function. So this range has to be your domain of the inverse. So my domain of the inverse has to be the bracket 4 to infinity, and my range of the inverse has to be the negative infinity to 3 bracket. So back to looking at the graph of the g inverse and how we talked about they did not graph the whole parabola, they just did half of the parabola, and the reason they did that is because of this domain restriction. So if your range here is the same as your domain for your inverse, that's actually only half of that parabola. So they are basically going to the vertex of that parabola, and they're chopping that parabola right in half and just showing that side of the parabola that is the inverse function of g of x. So you have to be a little careful when you're finding inverse functions, because this inverse function here is actually only valid for x values that are greater than or equal to 4. So you may see that written beside an inverse function from time to time, and that is where they are indicating that the domain was restricted. So going on to h of x here, you can see we have a very similar situation to what we were just dealing with. And the h of x function is a quadratic, but they have limited the domain. So I can go ahead and write that the domain of h of x will be 1 to infinity with a bracket on the 1, because they have established the domain already for us. So let's now go ahead and find the inverse function. And so this here is my inverse function of h of x. So now what we can do is we can think about that we got a square root function. Okay, and like I said, it's kind of the exact opposite of the previous example, how we're getting, you know, these two functions related to each other between the quadratic and the square root. So if you look at your graph down here, so let's see, I believe that this reddish one is the h of x, and then the bluish one is your inverse. Okay, and that's how each of those graphs look. And so you can think about, for your h of x function, you already knew the domain, and if you think about that vertex down there, the range is going to start at 2 and go to infinity, and then that gives you your domain of your, sorry, this should be a -2 here, excuse me, -2 to infinity, and so that gives you the domain of your inverse function, which will be -2 to infinity, and then your range needs to match the domain of the h of x, so that will be 1 with a bracket to infinity. All right, so on this last example here, I want you to give it a try, all right, on your own. Pause the video, see if you can get to that inverse function, then play the video and see if your work matches. Okay, so you can see here where I have taken the f of x function, and I have gone through the steps of finding the inverse. And I switched my x and y, as you can see there, and then you're solving for y. I wanted to show you that here basically what I did was multiply both sides by this y minus 2, and that cancels the y minus 2. And then at this point, then when you're looking at on the left, I divided both sides by this x, and you can see that cancel the x's on the left, and then I only had to add the 2 over, and so I get down to this version for my inverse function. Or, okay, some students at this spot here would distribute that x in, and you would get something like this, and then what you can do is add this 2x over to the other side, and then you can divide everything by this x, and you could write your inverse function like this. And both answers are fine, and like WebAssign would take either one, and so both answers are equivalent to one another. So let's talk about the domain and range. So if you go back to your f of x function, we know that x cannot equal 2, so our domain must restrict that. So we must say -infinity to 2 union 2 to infinity. And that actually tells me the range of the inverse. So I can go ahead and fill that in over here. All right. Now, as far as figuring out the range of my function, it's actually easier to figure out the domain of the inverse. All right. If you go back and look at your inverse, then we can see that x cannot equal 0 there because it's in the denominator. And so your domain of the inverse is going to exclude the 0. And then that in turn would give you this range of your function. Okay, so sometimes you have to get a little creative with figuring out the domain and the range, but just use what you know about your inverse functions, and you usually can figure out both the domain and range for each of the function and its inverse. So keep working, ask questions. I'll see you in the next video.